Okay, so this is the moment of truth. Yes! Hello and welcome to a video I've been looking forward to for quite a while. So here's my homebrew CPU as it currently stands, and this is a little LCD module that's been my primary display for quite a while. So this is my prime number finding sieve of Eratosthenes code. I think this is the most complicated piece of code I've written for the CPU so far, predominantly because there's a multiply and divide and a bunch of clever table handling functions in there. I know some people are interested in how the incremental sieve works, so if you are interested in that, drop a comment in the description because I'm open to doing a video on it at some point. But let's fire this up at full speed. So the CPU is currently clocked at 1 MHz and it's very stable doing that, and I'm really pleased, although I have had it run at a higher speed. So this is completed quite quickly, but even at 1 MHz, this is mostly capped out by the time it takes for the LCD to respond to data. So I end up in a loop waiting for the busy signal all the time. Also at the start of this project, I said what I'm really interested in doing is writing some games. And I have done the basic text mode snake game, Snack, but that's not really what I meant when I said that. What I really want to do is some proper graphics VGA output, and this video is the first part of my VGA series. Now I've made up this cable, which is a VGA connector and then a DuPont style set of wires that will allow me to plug this into a breadboard. But let's talk about what I'm going to do. Okay, before starting, I think it's worth setting some project goals. Now I've talked about VGA, and I've seen a lot of VGA projects out there that run at a subdivision of the basic resolution. But my first and foremost goal is I want to run my VGA at full resolution, 640 by 480 pixels. And this isn't going to be easy, especially if we don't use any specialty ultra-fast parts, because to achieve that we'll have to drive some of the basic TTL components up towards their top rate. And we need to get the circuits right to do that. But doing this on a display circuit is actually the best place to experiment with pushing components to their limit. Because once we've got the circuitry for the synchronization correct, any timing errors that we have in the rest of the circuit should just manifest as visual glitches rather than a crashed processor. So this is actually the best possible place for us to experiment with trying to run circuitry at a faster speed. Now visually, I want to be able to update this at the full 60 frames per second, get some really cool visuals going. I have said many times that what I want is to do some game development for this, and I want those games to look cool. So something I want to do is implement hardware scrolling. Now when you stop and think about that, it's not that difficult, but we'll get to that in a few videos' time. But one of the things that is going to need is a way to specify scrolling indexes, and that's more than we've got I/O ports for. So one interesting thing I'm going to have to do just to implement that is implement some memory mapped I/O, which I know some people are interested in, so that should be quite interesting in and of itself. Another thing I'd like to implement to get some nice fast moving graphics at 60 frames per second is some sprites. Now I've had to think about the hardware necessary to do this, and it very much becomes a replication per sprite, particularly when you're running things close to the maximum speed. So I think what I'm actually going to do is implement one hardware sprite and then use some trickery to get more than one out of it. Now when working on 8-bit hardware, one thing that people always used to talk about was how many colours things would have. I want millions of colours in this. What I'm really talking about there is a 24-bit DAC, so I can display 16.8 million colours. I'm obviously going to need to be able to implement some kind of palletization in order to achieve that. And the last big goal is to have minimal CPU impact. There's lots of ways that I could implement this display that would consume the processor, but I didn't build a pipeline CPU so I could waste its cycles. I want to be able to put some really interesting work into updating the display, and so I need to keep the CPU actually free for doing that. Now, when I'm all done, I will write a couple of basic games and probably some visual demos to show off the capabilities that'll be more kind of prototypey. Let's kind of set some lofty goals for what I'd like to achieve. Now, with the hardware scrolling and sprites, it'll be nice to get something with a bit of Super Mario-esque gameplay. Probably have some better graphics than Super Mario though, because we are going to have higher resolution and more colours. But I've got one special goal that I think would be quite an achievement. So the 8-bit computer I spent most of my time on was a Sinclair Spectrum, and at some point I progressed onto a 8086 based PC. But along the way, some of my friends got Commodore Amigas, and I believe it was in 1984, there was a demo released for the Amiga, which was very impressive. It really kind of changed people's expectations on what microcomputers were going to be able to do. It was the bouncing ball Boing demo. Now, the Amiga was really a step beyond the 8-bit era, but once I look at all of these features that I'm planning to add to the VGA display, coupled with the performance of the processor, I think I've got a pretty good chance of being able to reproduce something visually like this. And so that's my big goal for a demo at the end once all is done. You can judge how well I do when I'm finished. Well, let's talk about the VGA signal we need to generate. When I was a kid, I remember looking at the two wires coming out back of my Spectrum, wondering how it could possibly represent a two-dimensional image. But of course, what it does is it actually just scans from the top left, a line at a time, all the way down to the bottom right. Now, this isn't entirely visible data if you consider this as the progression of time. Only a subsection is visible data. In each horizontal line, you've got a visible region, but you've also got a non-visible region called the horizontal blanking interval. And at some point inside that, you've got a sync signal. So this will be the horizontal sync line, goes low for a predefined period of time. And that's what allows the circuitry for both the display and the monitor to keep in synchronization. So sections of blanking which aren't sync are called the front and the back porch respectively. And then at the end of the frame, there is a section known as the vertical blanking interval that has a vertical sync, and that also has a front and a back porch as well. Now, the exact time interval for each of these sections is dependent on the resolution, and we're going to go for 640-480. So, as we mentioned before, that's a 25 megahertz pixel clock, but we've got 800 horizontal pixels, 640 of which are visible, and then 160 are the front porch, sync and back porch. Now, the first VGA displays were cathode ray tubes, and the scanning was done by an actual electron beam. And so it was necessary to have these chunks of time in order to get the beam swept back to the start of the line to start drawing the next one. Modern LCDs don't have that limitation, but the signal structure has remained the same. Vertically, it's similar. We've got 525 pixels, 480 are visible, 45 additional scan lines for the front porch, vertical sync and back porch. Something I spotted it's worth taking note of is that all of these horizontal numbers are actually multiples of 16. And I think that's going to be quite handy in a couple of stages of the project and keeping things simple. Particularly when we build the sync generating circuit, we can run that circuitry at a fraction of the full pixel rate, which should make our life a little bit easier. So lastly, I'd like to talk about the process of building this thing before we actually get started. This is going to be a fair few videos. Don't expect this VGA sub-series to be done in a couple of weeks. There's going to be quite a lot of work here. I strongly suspect we're going to have to turn parts of it into PCB before we're done, just to get the circuitry responding fast enough. And all the features I'm looking to include it's going to be quite a lot of circuitry. Now, one of my goals is to have a visual improvement of some kind in every video. We'll see how well I do on that, but I definitely think I can do that for the first few. But that is going to mean starting as simple as possible. And so I have spent some time sat around thinking about what is the simplest possible circuit that I can build that would generate a VGA signal. Now, there are some fairly simple circuits out there, but I think I can do something really quite clever. The 8-bit pipeline CPU we've built is actually pretty powerful, and so I think we can make use of it in order to get the simplest VGA really simple. Because what we really need to do is do lots of counting of pixels and lines, and we need to output some data. And these are, counting things and outputting data is things the processor can do already. So I sat there and thought, what is the minimum circuit that I could add to the CPU in order to give it the capability of generating a VGA circuit? And I came up with my answer. It was just one chip and a few resistors. So what we're basically going to do for the first step is generate a VGA signal in software. I've already done a test and found I can get a 25.175 megahertz crystal running in the clock PCB. Now I have to use quite a high clock divider of 8 in order to make the processor stable, but that means that I've got 100 clocks per scan line, and I think that's enough to get something visually interesting out onto the display. Resulting VGA output is going to be rubbish, but it is going to be a performance flex for the CPU. And I think it's going to be really cool if we can kick off with such a basic circuit that actually works. Let's go and build it. Okay, I always like starting on a fresh new breadboard. Now this cable, that's red, green, blue with ground either side of it. And then the green and the yellow wires are horizontal and vertical sync respectively. So my theory is I can get this all working with just this one D-type latch chip. So we want to pull output and enable down permanently, but then we want the load line to come out and go to the load line from one of our ports. So there. We may as well power our circuit from this directly. When I come to convert some of this to PCB, I want to put some circuitry in to isolate the power and ground rails from the rest of the CPU because they're quite noisy. So that'll be our control connection back to the CPU. I'll need to dig out a cable for the main bus, which will come in here, but we should have a register we can load, and then we want to output the signals to the VGA. Now I've got 3 separate grounds here. Now these are all going to end up connected together, and on this breadboard I'm just connecting them straight to the ground rail on the breadboard. And whilst eventually we always want to do that, on the PCB version of this I believe we want to pay some attention to the routing and keep the individual grounds that come in on the colour rails together with those lines as long as we can. Now, everybody says you need to connect the sync lines up via 22 ohm resistors, or resistors in that general area. So who am I to argue with that? Now for red, green and blue we want a basic resistor ladder. So these are the closest values I had to 400 and 800 ohms. Now, I am going to get hold of some of those resistor arrays and see if I can get appropriately valued ones for the R2R ladders, because that will probably make the larger size ones a lot easier to manage on breadboard. Or we might end up converting the DAC component to a PCB very early. I'm going to try and colour code these well. Least significant red bit and most. Same for green. Okay, I think an LED on this load line is going to be handy if we have any problems. Active low, so I'm taking that to the 5-volt rail. And I think throwing some capacitors on here is going to smooth it out a bit. In theory, that is everything we need to get the most basic form of VGA working. Let's get the CPU out and see if we can make it do anything interesting. Okay. Going to go in there. Don't want the prime numbers code anymore. And I've got 25.175 megahertz crystal. Now we're never going to be able to run the CPU at that rate, but we can set the clock divisor to be something a bit more reasonable. And I did test this a little while ago and I managed to get it stable at 3.14 megahertz. Okay, gonna need a bus connection. Okay, so first up we need to implement the support for the VGA register into the pipeline ROMs. Okay, I did free up a couple of instruction spaces. So to implement this simple circuit, we just need the out. But I'm going to add the in at the same time because that will save us having to change the ROMs in the near future. Okay, so now we need to implement those instructions in the control build. So we put the VGA into device port 10. Okay, implementing these should be pretty easy. So this is exactly the same as all of the other I/O functions. So for an output, we are asserting the A register to the main bus and issuing a load to the VGA device. For an input, we tell the VGA device to assert to the bus and we load A. And that just changes the ROM for pipeline stage 2A. Okay, now we're going to need some test code. Okay, I don't want to jump straight to generating an actual video signal. Let's just see if we can generate the horizontal sync. Now, software generating sync signal is going to be pretty difficult. We're going to need to be very precise. Now, 640 pixels divided by 8 is 80. So I'm going to put 80 nops in for that first bit of image data. Now, the front porch is only 2 cycles. Constant load is 2 cycles, that's 1. So that's a 3 cycle operation. Let's make our lives easy on the timing. Right, so now we're into the sync. That needs to be 12 cycles long, so we've got 12 nops, but we need to subtract from that whatever it takes us to output it. Now we've got 6 cycles of back porch. I think that's 3 cycles, so 3 nops should round off a line. Now, this kind of cycle counting to create precise timing is kind of fun, but it also gets very tiresome very quickly. So it'd be nice to get hardware to handle all this sync generation as soon as possible. But let's see if this works. Okay. I will speed up that copy sometime soon. I'm going to get the oscilloscope on so we can check the timing. First up, let's see if we can check that the clock is running at the speed we expected. There you go, 3.14688 megahertz. Right, now the little LED seems to be flashing. That's actually the kind of pattern we would expect. So that was the horizontal sync line. Okay, so the correct horizontal sync time is 31.469 hertz. 31.469 kilohertz, and we've got 31.468, and actually 469 would be the legitimate roundup for that. So I think that code is bang on. Our transitions here are a bit noisy. Slightly better. But it's likely we won't be able to get a really clean signal until we've actually got a PCB with this circuitry on it. Okay, I wasn't going to force you to watch me code this, but I've spent quite a lot of time with quite a bit of trial and error getting this going. But I will give you a quick tour around the code and explain how I did it. Because making all of this cycle perfect was not easy. Firstly, what I've got is a table with 1 byte in it for every line in the signal. So if you see here, I've got 480 duplications of the address of line standard, 10 of line V blank, 2 line V sync, another 32 of line V blank, and then 1 of line reset. Now these are 8-bit pointers because I managed to fit these little sub-functions into a 256-byte block. So this is basically a pre-calc table of pointers to functions. Now these functions are down here, and they basically generate the correct output for each of these different line types. So line standard, I have unrolled out this ultra basic loop of load string byte and then output it to the VGA. So that's reading from this solid block of binary data here, which is an image I've converted. Line V blank, this is very similar to the code that was output before. This has a appropriate delay loop in it with a series of NOPs. But in all of these, I set A and B to be the variable before the horizontal sync pulse and the value that it goes to afterwards. And then in my common main loop code, I output those signals. And then line reset is a special case one, which is pretty much the same as the horizontal blanking line, but it also resets my pointers for both indexing this table and indexing the image back to the start. I think we should fire that up and take a look. Okay, so this is the moment of truth. Yes! Right, okay, so this parrot, the rendition of it is absolutely terrible. We've got 24 pixels of horizontal resolution and probably not the best color reproduction at all. I'm seeing some banding vertically here, which I suspect, because the way it lines up with the pixels, I suspect that's probably just noise on the power rails. So we're going to want to experiment to see if we can clean that up, which I think is mostly going to mean isolating the VGA circuit as much as possible from the CPU and its noise production. That is absolutely awesome though. Okay, now this is the simplest possible VGA implementation we could do. It's one chip and 8 resistors. Can't get any simpler than that. I'm really chuffed this worked. But what I think we can do is go through the next few videos, adding to this and taking workload from the CPU and building dedicated circuitry for it. And of course, what that means is we're going to be able to do more impressive stuff and free up the CPU to do some interesting work of its own. But I'm really pleased we managed to get this ultra simple circuit working in the first video, because I think that's just going to make the whole series a lot more interesting. Right. I hope you found this interesting. I'm really eager to get on and start work on the next bits. But yeah, hopefully I will see you again soon with a bit more. Thanks for watching. Goodbye.